Okay, so let me go ahead and get started here. Let me double check audio, all that stuff. Looks like it's working from my end here. We're going to go over the hands-on exercise 3 here. Let me bring this up to remind us what we're going to be looking at then. Okay, so we're going to be looking at some longitudinal ordinal data. The scenario here is we've got our phase 3 confirmatory trial for our potential treatment for cystic fibrosis, and during each visit of that trial, and they occur on an every 4-week basis, as I recall, the patients indicated whether their health-related quality of life, which we just called HRQOL, whether it was worse, unchanged, or better than it was prior to the trial. And so what we're talking about then is a 3-level ordinal scale, in this case going from worse to better. And well, we'll show you the exploratory analysis, but here it says that it suggested that the HRQOL initially worsened for those patients assigned to our MI2 compared to placebo, but it improved over time, and we're going to explore that relationship using a longitudinal cumulative logit model. So let's just remind you the design. It's a parallel design. There's just 2 treatment arms with 250 patients per arm. We've got our multiple doses of MI2. Those 2 treatment arms consist of a placebo arm and a 40 milligram per day arm for MI2. And again, our HRQOL measurement is a 3-level ordinal scale that's reported every 4 weeks. So we're going to construct a model for that. Showed you last week, I believe, there on Monday, that is, what the scores look like here. Here we're looking at the different score levels over time for the 2 different treatments. So you can see we've got red is worse, black is unchanged, and green is better. There's our 3 levels of the scale. The left-hand panel is our placebo group, and we're plotting fraction of patients on the y-axis, time in weeks on the x-axis. So we can see that if we look, for instance, at unchanged here, we can see that roughly 50% of the patients pretty much right from the get-go here sort of sit right at the unchanged pretty much throughout the trial. And then we have about 20% of the patients report being worse, again pretty much constant throughout the trial, and then about 30% report feeling better. Again, staying roughly constant over the trial in the case of the placebo treatment. Then for our active treatment arm, our 40 milligram per day arm, we got our unchanged here starts out in a similar place to placebo, but with a bit of an initial bump upwards, and then over time that seems to fall off a bit. Then we have, in terms of patients reported and feeling worse here, we actually have a fairly substantial bump upwards right at the first visit compared to the placebo. So it's upwards of around 35% here compared to 20 for placebo. But then it falls off so that it eventually falls below what we see with the placebo group. And then finally, when we look at those reporting feeling better, initially that's lower than it is for placebo, but gradually rises over time until that seems to be the highest or the largest group of the 3 here. So in the end, we have, the large majority of patients are reporting feeling either the same or better at the end of the trial. And this is just looking at this in the same data in a slightly different way. We're looking at, on the left-hand pair of panels here, we're looking again at fraction of patients per time, but now instead of looking at the fraction at each score, we're looking at it as cumulative scores. So we're looking at those patients who are worse. So that's the group where it's less than or equal to 1. Well, it's actually 1 because there is no score less than 1 here since we're numbering 1, 2, 3. And then we have less than or equal to 2, so that's the combination of people worse or unchanged. The reason for doing this is because in our model we're going to be modeling in terms of these cumulative fractions or cumulative probabilities. So these are more closely related to those, and you can see what the pictures look like here in terms of down at the bottom you have the group that's reporting worse, and then up here is either worse or unchanged. And the same thing is now in our model we're going to be using a logit transformation here. So the right hand two panels here are exactly the same data but logit transformed. And because we're going to be writing our model in terms of that quantity, it gives you some exploratory look at it in terms of, gee, what kind of a function, for example, might describe this kind of information. Other things we can start doing is start getting a handle on whether some assumptions like proportional odds, or whether or not assumptions like proportional odds might hold in this case. And this starts giving an indication, but I actually added a couple more slides, not slides, but a couple more plots to the exploratory plots. Let me actually pull those up here. First couple pages are the same ones we just looked at here. But then I did, let me make sure I know, yeah, okay. Then I also actually calculated the odds, or the observed odds. So in this case, that's going to be the fraction of patients divided by 1 minus the fraction of patients. And recall, if we go back in our, let me go back a couple of slides here in our discussion about these kinds of models, I guess a few slides. Okay, where's that discussion? Here we go. Recall I commented that the cumulative logit models, which are going to be the ones we're going to be working with here, have the property of proportional odds. And this slide described a couple of the consequences of assuming proportional odds, and it is an assumption in this case. You notice that if you take the odds, if you take the odds for one score level, let's see, actually I'll use the words I actually did before. So under proportional odds, the cumulative odds ratio for the same score for two different sets of covariate values ends up being independent of the score. And then similarly, if I ask the questions, well, what if I take an odds ratio for different scores at the same set of covariate values, and that ends up being sort of a similar thing, it ends up being independent of the covariates. And there we can take some graphical looks that in effect test whether or not these things hold. So for example, here what I've done is I've just taken the log odds for our case and plotted them versus time for our cumulative fractions here. And now in this case we're talking about for the two different scores. So this is like up here now, and now if I make an assumption that on average the covariates are about the same for these two groups, and actually we could check that, but I didn't in this case, but I believe it is at least approximately true here. What we would expect under this then is, okay, it's saying that basically that the ratio should stay the same. Well, in terms of a plot like this, where I've taken the log of the odds, so if the ratios are the same, then that means if you take the log, the differences should be the same for our different covariate values here. And if you look at this, so basically as we're going across weeks here, we're talking about different covariates. And so the question is are these differences here between these two curves about the same? And I didn't. I probably should have calculated those numbers and put them across, but at least on a rough glance here, that appears to be roughly true in our left-hand panel, and I'd say it's roughly true on the right-hand panel, with maybe a quibble over the first time point there, which looks like it might be a little smaller. So at first glance, proportional odds is probably at least approximately holds here. And we can turn this around different ways. Similarly, when I look at here, what I'm looking at now is I've just taken the same data and turned it around a different way. Again, I'm looking at log odds on the y-axis and time on the x, but now the panels I've broken out here are for the different. Oh, you know what? This is mislabeled. Sorry, this should be dose. Okay, so I need to fix that in the scripts there. Anyway, this should be dose on the x-axis. Of course, we only have two dose levels. We have 0 and 40 in here, and so now what I'm looking for again is I'm asking the question: are these lines parallel? In this case, or said another way, are the differences between the less than or equal to 2 group and less than or equal to 1 group roughly the same for those two doses? And on average, that appears to be approximately so again. Okay. Okay, let's see. This is looking at it in a little different way, and this in a sense relates more to the second identity here, where now what I'm looking at are, I've turned it around where I'm asking sort of this question: what happens if I take the odds ratios for the case where I have different scores, but but the same covariates. Is that right here? Yeah. But anyway, what I'm looking for in this one, again, I'm applying log odds, but now the x-axis are our two different scores, and the different curves here correspond to the different doses. And again, what I'm looking for is to see if these are at least approximately parallel. And again, that appears to be largely true here. And this is again turning that around, just breaking up the panels here. So I've got the different lines correspond to different times. The panels now correspond to doses. And again, I'm looking to see, do these things appear to be remain approximately parallel? And again, they do. So at least on a crude level, it looks like the data appears to be consistent with an assumption of proportional odds in this case. Was that the last one? I think so. Yeah. Okay, so that gives you some idea of some exploratory sort of plots that you can do to try and get a handle on whether the model assumptions might hold. Okay, let's go back on down. Okay, so I've got a proposed model. Let's take a look over it again. Where am I? There we go. Okay, so again, it's going to be a cumulative logit model. Our likelihood for our QOL, and again, QOL is now going to take on values of 1, 2, or 3 in here for, what was it, worse, unchanged, better. That's going to be categorically. We're going to use a simple categorical distribution, which in effect is just a sequence of probabilities corresponding to each possible score level. So this P here, this Pij, is going to be for each Ij, for each I and j, is going to be a set of 3 probabilities that sum to 1. In here, for any one of these, what I call PM sub ij, so that's going to represent the probability that our QOL on the ith visit for the jth patient equals m, where m can be a value of 1, 2, or 3. So we've got that. Since we're going to write our model in terms of cumulative probabilities, I rewrite that in terms of the difference between the probability of QOL being less than or equal to m minus the probability that it's less than or equal to m minus 1. And recognize that when we get, in this case, where if m is equal to 3, recall that the value has to be 1, 2, or 3, so the probability that QOL is less than or equal to 3 just equals 1. So when we're done with this, we really only have to worry about 2 cumulative probabilities, because the third is determined by difference. And then our model is going to be in the form then where we've got the logit of the probability of our QOL being less than or equal to m is going to be an intercept term here. Just call it alpha m, so it can take on a different value depending upon what the score is. And then in our proportional odds model, the rest of the model will be independent of m. So I've got this as, recall when we wrote this in the general terms, we always said like alpha m minus f of x and theta. Well, our f of x and theta component then is, I've written out here in terms of a placebo effect component and a drug effect component plus a random effect, which is going to be subject specific. Since we do have multiple values for each individual, we have the potential for estimating such a random effect. For the our placebo here, well, when we look at the data over here, okay, it's actually, you know, my temptation would be to just assume that that the placebo effect, if anything, would be, you know, would probably be 0 in this thing, because it doesn't change over time. But I allow for the possibility that maybe there's some effect, and in this case I just use a simplistic linear model, so about as simple as we're going to get for something that might change over time. So we did that, and then so that's all I've got here, this beta times our time. And then for the drug effect, I've got over here a possible initial effect plus a more gradually increasing effect here over time. And if we look at the data over here, you know, that initial effect is suggested by the fact that when we look at, you know, at both of these over here, they, you know, that are at the earliest time, now they're technically not at 0, they're at 4 weeks, but it, you know, it is suggestive that we've got some initial bump upwards. Whether that really begins immediately at time 0 or not, I suppose is debatable, but that's essentially the way we've modeled it. I've proposed the model here. And so we've got that initial bump up, but then we've got a decline over time, which is captured by the term here, the R1 minus e to the minus kt, you know, with some magnitude associated with that, captured by the b. And then finally, our random effect is just going to be a normal centered at 0. Stuck just weakly informative priors on everything. Now there's certain things that need to be true. In particular, we have to put an order constraint on these alpha terms. So we need the alpha 2 to be greater than alpha 1 in particular. So the way it's set up here is alpha 1, I put just a fairly flat prior covering the whole real line on, and in fact alpha 1, at least in theory, could be anywhere in the real line. But for alpha 2, what I do is, instead of parameterizing it in terms of alpha 2 directly, I parameterize it in terms of the difference between alpha 2 and alpha 1. And what I do is I used a truncated normal where I just allow the positive portion of that truncated normal. Alternatively, I could have used a log normal. It would be another fairly natural choice to use for something like that. Or you could also make an argument for maybe a uniform that starts at 0 and goes up to some fairly large number. And then finally, pretty much everything else is fairly straightforward. I allow for beta A and B to be pretty much anything, and then I restrict K by using to be positive by using a log normal, and also restrict sigma to be positive. In this case, I used a uniform. Okay, so that's what we're going to implement. So let's take a look at the implementation process here. Let's see, where do I want to start on this here? Let's see, showed you the things. Well, one of the things, let's go ahead and pull up the R script here. Much of which is going to be a lot like the other R scripts you've seen up to now. Again, you can sort of use them as boilerplate. The past ones as boilerplate for this. Okay, let me make that a little bigger. Okay, and actually even before we look at that in any detail, let's open up the data set so that you actually see what we're building on here. Okay. Okay, so the data set's a fairly simple looking thing since we didn't capture a bunch of covariates in it or anything. So we've got a patient ID value here. In this case, it's just simple integers. It looks like I already set them up as integers starting at as an integer sequence starting at 1. We've got the dose, which is either 0 or 40 milligrams per day in this case. We've got time in weeks, and our QOL measurement. So again, you can see it's either values of 1, 2, or 3. And you'll see various patterns over time with that. Like here, you've got a patient who is, most of the reports say unchanged with one worse and one better in there. You got another one who starts out saying they're worse at the first visit, but then they're stay pretty much constant or unchanged after that, and so on. So that's the data we're going to be working with. Okay. Actually, you know what? Let me leave that up here so that we remind ourselves what the names are as we work with the data. But we can shrink this down a bit here. Sort of stick it off to the side. Okay, so the script is same old, same old. We've got the name of our model in here. Let's see, we pull in various, actually I don't think I use locfit in this case here. I notice I have that in there, but we've got our various libraries pulled in here. We set up all our path names and that in here. Here you can, whoops. Here you can see where the data is getting read in from the file we just looked at. So that takes care of that. The exploratory plots you just saw, if you wanted to see how to make those, that's going on right here in this section. You can see where it's opening up a plot file here with the PDF statement, and then you see the process here of generating those. Now recall the data is in the form of our raw scores, but the plots I was making were usually in terms of fraction of patients, either at a score or at a score less than or equal to a certain value. So you can see the use of the aggregate statement inside here to construct those fractions of patients. So you can see how that process works in here, and then the resulting lattice plots that are done to expose that. So if you want to get a handle on that process, that's there. Okay, so we're going to create the our data set. Data set's almost in the form we needed in already. The only thing I allowed for was the possibility that maybe the patient's row in there, or the patient column, was not the exact integer sequence we need, and set this up to change it into one if need be. Actually, it was already. This was kind of redundant in this case, but we did it nonetheless. We're going to want to pass things like how many observations. Because we're going to be dealing with a random effect in here, the model's going to need to know how many patients, because we're going to have to set a loop to create our random effects. So that's taken care of here. Then we need our patient identifier, our time. One of the things that we're going to want to be able to do, recall in, let me point this out, notice here I've got this, what I wrote as an indicator variable for dose being greater than 0. Essentially that means whether or not they're on placebo or drug in this case, and I also included such an indicator right here in this line, and you can see here how I've just used a little bit of a trick. It basically does a logical statement here which will generate a logical term which under the hood is essentially a 0 or a 1, and convert it to a numeric, so it gets passed as an appropriate numeric to WinBUGS. And then finally our quality of life score going in here, and that's our data set. We've got our initial estimates, and I'll let you try and take a look and see how these were generated. Most of those I didn't do them particularly carefully. I just kind of did it by eyeballing the plots, particularly the plots in terms of the logit transform. So they were just kind of roughly eyeballed here to get those numbers. They could certainly have been refined. For instance, you could do just a simple, you could use the GLM function inside R to do a non-Bayesian logistic regression and probably come up with some of those numbers. Okay, so let's see. Then I'm going to tell it what parameters I want in here, and actually we need to decide what we're going to, actually I didn't even mention that. One of the things we're sort of deciding right here, it appears we're deciding what do we want to call the parameters. So you can see that process is going on up here. So I've named them, so when we write the model we're going to have to continue these naming conventions. So I used alpha, beta, A, B, log K, and sigma, which roughly correspond to the names that you see on the slides. And then I'm going to say what parameters am I going to want to be looking at for our diagnostic plot. So I've got alpha, beta, A, B, K, and sigma. Then we'll also want to be able to monitor some others to do some diagnostics. And in particular, I'm going to grab the eta, which is going to be our individual specific random effects, and then our individual and population prediction values in here. I could imagine you might also want to calculate some of the probabilities too, but I think for most of our diagnostics this will do the job. And then we just set it up. When I originally ran this, I did it with sort of my typical, 3 chains, 10,000 iterations, 4,000 burn-in, thinning. I usually do either 5 or 10, something like that. We'll see in a bit that appeared not to be adequate, and I bumped that up a bit. But we'll take a look at the results after we look at the model. Okay, that's far enough, I think, to start talking about constructing our model. Let's go ahead and build this model. Let me fire up WinBUGS here. Come on, there you are. Okay. Let's open up a new thing here. Let's make the font big enough that you might be able to see it. Maybe widen this a bit. Okay, so as usual, we start out with model. Actually, let's maybe make that a little bit bigger too, I think. Oh, that's interesting. Let's go to 20 maybe. Okay. Okay, now one of the first things in here is we're going to have a random effect in here that we're going to have to make use of in our model. So I could either do it at the end or at the beginning, but let's go ahead and do it at the beginning. So let's set up a loop that goes over our individual patients and generate these eta j's here. So let's just go ahead and let's say for I in 1, 2, what did we call it in our script here? Did I call it n patients? Okay, going too fast. Let's see, n patients with a capital P. Okay. Okay, and so we're going to want to generate those etas. Got our squiggle, they were normal, centered at 0, and with some precision we'll just call it tau. Okay, so that'll take care of generating our random effects. Then we're going to go ahead and loop over our individual observations. And what did I call it? I called it nobs, no capitals. Okay. Okay, and let's start out with our first component here, where we're just going to have our categorical value here. I think I used a lowercase QOL for the data. Yep. So we're going to call it QOLI and tilde, and then it's dcat for our categorical distribution with our probabilities, which, okay, they're going to be specific to each observation because they vary as a function of things like time and dose. So got to have an I in there. But then there's going to be 3 values in here corresponding to the 3 different possible levels of QOL. So I've got to put in the 1 to 3. Oops, I needed to have a closed square bracket there. 1 to 3 in there to make that work. Because really what dcat takes as its argument here is a vector of values. So, and that's what we're giving it. We're basically giving it 1 row from a matrix out of here, but that 1 row is interpretable as a matrix, or I'm sorry, as a vector. Okay, so we got that. Now we have to generate our individual probabilities, all 3 of them. So we've got like PI1 in here, but keep in mind we're going to be writing our model in terms of the cumulative probabilities. So you can see here where we're going to write our model in terms of that cumulative probability. But first we're going to have to write out our individual probabilities in terms of that cumulative, and that's basically what you see going on up here, where I have this PMJ equals, the difference between the cumulative probabilities. So I'm going to just call that PCUM I. Well, it's going to be 1. And, well, now the probability that the score is less than or equal to 1 is equal to the probability the score equals 1, because there are no other values below 1. So we've actually finished that statement. But then for the second one, now we're going to have to talk about the cumulative probability. For 2, so that's the probability that the score is less than or equal to 2, and subtract from it the probability that the score is less than or equal to 1. Okay, and finally we need the third one in here. Okay, which is the same pattern. In fact, if you want, you could just be quick and dirty here. I'll just take that. I'm going to copy it here and just change these, 3 and a 2. So I'm taking the probability that the score is less than or equal to 3 and then subtracting it from the probability that the score is less than or equal to 2, and the difference should be equal to the probability equaling 3. Now we can actually simplify this further, because there's only 3 possible, the score can only be 1, 2, or 3. So the probability that the score is less than or equal to 3, well, that's a certainty. It's 1. So we actually don't even need to worry about PQI3 here. We can just replace that with a 1. Now we're done with that part of it. And then we have to take care of our statement here in terms of, not quite what I wanted to highlight. I guess it's not going to do it that way. Okay, so I'm going to have my logit of my probability here then is going to be this thing on the right, or alpha m minus e placebo, e drug, and so on. So we can go ahead and do that. In fact, we can put it, WinBUGS lets us put a logit on the left side here. Okay. Now we have to do it for each one of those. So I could actually probably be sneaky and put this in a loop, but let's go ahead and do it. Since we've got so few levels, I won't use a loop here. So I'll say PQI1 then is going to equal, well, we've got to have our alpha. Okay. Call it alpha, so it's going to be alpha 1 minus our E placebo, which could be different for each observation, plus our E drug. Also need to index that on I. Oh, I didn't want it to do that. Let's see if we can get it to. Let me change this. There we go. Okay, plus eta. But I can't call it eta I because there's only 1 to n patients of those. I have to index that on patient to grab the corresponding eta I. And I gotta close that all off with parentheses. So that takes care of our first one. Again, I'll be lazy here. Let's do let's copy that. And so I can say for 2, this is going to be like alpha 2, and the rest of it would be the same in here. So that will take care of that part of it. Let's see. And I don't need to do, recall I don't need to do a PQI3 because again that's just equal to 1 anyway, so we don't need to do any further calculation. So we're actually done with that part of it. Okay, we just have to generate our E placebo and E drug components here. So let's go ahead and do our E placebo. Which was what? That was our beta TI. So we're going to have beta star, I think I just called it time I. Okay, there's our placebo effect, and then for our drug, okay, so we've got our indicator or flag that takes on value of 1 or 0. multiplying this term over here, a plus b times 1 minus e to the minus kt. So let's do that. So we've got, recall we defined that I drug, an index, and then we've got an a plus b times 1 minus our exponential of minus, what did I call it? Did I just call it k? I think so. And where'd it go? Yes. Okay, and times time. Also indexed by I. Okay, so did I get all my parentheses? I got one with that, and I need one more. Okay, so I think that takes care of our drug. I think we've covered our likelihood here. What am I missing? Anything? No, I think that's everything. Okay, so that closes out our for loop there, and then we need to deal with our priors as part of this in here. So we have to go through all of our components in here. So for example, we had our alpha, alpha 1 we'll just use our d norm 0 1.0 e minus 6, again reminding you that everything is in terms or not everything, but the normal distribution is parameterized in terms of precision instead of variance. Now recall that our trick here is we're going to use a truncated normal to deal with the difference between alpha 2 and alpha 1. So why don't I just, there's different ways I could do this. I'm actually going to do this slightly different than I did in the solution I've posted, and then I'll give you that solution in a minute. So I could do this as, I don't know, what did I just call it, d alpha here, and that's going to be, that's also, in fact I'll just copy and paste this. So the difference is going to be that, except I'm going to, actually, is that what I did? Yeah, okay, that's going to be that, but then I truncate it to only the positive real line, and the trick there is to use the I function. Again, I'll put the lower bound of, I think that was an O of 0, and I don't put any upper bound in it. And that will do it. One thing I should mention is before you use this I functionality too freely, I do suggest you take a look at the help file associated with it. Technically, the I functionality in WinBUGS is intended to represent censoring, not truncation. It's just that in the special case where the parameters of the distribution are constants, in other words, they're not parameters being estimated in the process, they have to be constants. In that case, this does function just like truncation. So it's okay there. But if these parameters in here where I have a 0 and a 10 to the minus 6, if I had parameters that were estimated as part of this, it would not act correctly as a truncation. It would act very differently. So use it cautiously. Okay, and then we can just generate our alpha 2 indirectly from that. So alpha 2 then would be, what do I need? I need alpha 1 plus d alpha. Okay. And then we have a bunch of others. Whoops. Scroll that right off. There we go. Wrong window. There we go. Okay, so we got beta, A, B. In fact, let me go ahead. So we've got beta, A, B, log, and how did I write that in here? I did not use a capital. Okay, log K. Anything else that I'm missing here? Oh, and I've got sigma. Okay. Ooh, taking too much time by typing all this. Okay. So anyway, so in these we can do real quick and dirty because I can just grab this guy over here, copy it. Except for that one, which I said was going to be uniform. It's just dunif 0, and I think I said 10 to the 4th, didn't I? Yeah. Okay, and if I did everything right, that should be a representation of that model. In fact, let's do a quick check of the syntax by pulling down our model specification and hitting check, and it says model is syntactically correct. Okay, doesn't mean we're right, it just means that we're not wrong for syntactical reasons. Okay, now that's the core model right there. You've got your basic likelihood for your quality of life written in terms of cumulative probabilities. We've got our random effect in here, which ties into our individual observations down here, where we've called it here using our index or our nested indexes. So that's taken care of. So that'll do that. Now we probably also want to do some additional work here where we where we generate individual and population predictions. And rather than take up more of our time by doing a lot of typing here, I thought it was worth maybe stepping through this process to get the core model. But let me again do sort of our the Julia Child approach and pull up the baked one here. Let me pull up, actually I think I've got it over here already. Yeah, I do. Let me take a fully worked one. Let me make this bigger. Okay, here's one with all the bells and whistles added to it. So it's the same as we had almost, except for a couple of things. Let me first, the one thing is just a minor trick to knock out a couple of calculations. It's probably overkill because it makes it less readable, but I'll point out one thing is instead of writing the model as I did here, which is more closely akin to what's in the slides, where I have this alpha 1 and alpha 2 representing the different intercepts. The way I had parameterized it in the solution that I've posted for you is instead alpha 1 means the same thing it does here, but alpha 2 is actually what I call d alpha down here. So it's actually the difference between the alpha 2 and the alpha 1 that you see in the slides up here. And so when I did it, what you'll see is I do that same step right here, where for the first one for pqm I1, but for pqm I2, what I do is I just take pqm I1 and just add in the difference, which I just called alpha 2. So be careful. It's tricky because alpha 2 here is not the same as alpha 2 here. Alpha 2 here is actually the same as what I called alpha 2 minus alpha 1 on the sides. So all I need to do is take what I already calculated here and just add in that difference in here. So that's just being probably trying to be too clever since it makes it harder to read it, but that's what's going on there. Similarly, you'll see when it does the priors over here, as you can see, I see I centered it as 1 instead of 0, but whatever, is the alpha 2 here is actually the difference between the intercepts. So that's the one difference. The other difference is you'll see where besides adding in some descriptive comments in here, you'll see here's the individual predictions, which all I need is the one additional statement in here to generate those. Again, I called them QOL cond to indicate that these are conditional on that individual specific random effects in there. But then I also do the population predictions, which require basically redoing all the calculations using the simulated random effects, which you can see I added another line up here to generate the simulated random effects. So again, the distinction here being the individual predictions should be thought of as doing predictions of, too many O's, predictions of new observations in the same individual, whereas the population prediction is predicting a new observation in a new individual. Let's see. I think that's all the tale I wanted to tell about that model. I'm not going to run it here. If you do the 10,000 times 3 version, it's not too bad. It takes a few minutes. If you do the longer version, it does take quite a while. But let's take a look at what it looked like with the smaller number and then the bigger number to give you some idea of the process of that I went through in looking at this and trying to find ways to improve the performance. Okay, let's go back here. So actually I put it in something, yeah, this hands-on 3 orig here term. This is the one that's where I use the 10,000 iteration, 3 chains of 10,000 iterations. Let's go ahead and open that up here, just looking at the plots. Looking at our history plots, and what you start seeing here is for a couple of the parameters it isn't too pretty. So for example, if you look at particularly on this page, on A and B are particularly bad. You can see these sort of long-term trends in here. It's definitely not a fuzzy caterpillar, if you like. This is more the wiggly snake variety of shapes here. Now there's not a gross convergence problem in the sense that you don't see the chains widely diverging from each other, but it's still not good. You would have to, and then A in fact looks even a little bit worse. If we go down to the next slide, we see K is not very pretty at all. In fact, if it's hard, we don't see them on the same right next to each other. But if you look at A, actually if you look at all 3, but particularly A and K seem to be very heavily correlated with each other. In fact, we could probably just do a pairwise plot of the samples for A and K, and we'd probably see a very strong correlation if we did an XY plot of those. So that's suggesting that we may have at least some limited identifiability problems, but whatever's going on, that correlation between those parameters seems to be inducing a lot of autocorrelation and making it tough to get good estimates. If we were working in more of an optimization method, like a maximum likelihood method, you'd see this again. This is the kind of thing that might lead to things like the inability to produce a covariance step in NONMEM, for example. It just gets manifested differently in an EMCMC world. Okay, so it doesn't look so good. Well, one possible solution is just brute force. And the brute force in this case means do more iterations. So I said, okay, what happens if I do more? Actually, even before I do that, let me show you an additional diagnostic. Let's look at the samples, or the parameter estimates that come out of this. Okay, and the main thing I'm looking at is this last column, the effective N. And to get reasonably precise estimates around here, we're probably, we're looking for numbers in at least in the high hundreds and preferably in the thousands. And you can see here we have anything but that. In fact, we've got some that are less than 100. You can see for A, B, and K, they're pretty small, with A only being 32. So keep in mind this is for I think this is for what, 3,600 samples that are actually generated after we do the thinning, when we've got it down to being the equivalent of only 32 independent samples, which is nowhere near enough to make any kind of reliable inference in here. So, okay, now if I was going to do it by brute force and I wanted to get this to 1,000 for our effective n, I suppose I would want to shoot at something like take 1,000 divided by 32 and whatever multiple that is, multiply that times the 10,000 I did originally. I didn't get that carried away. I just multiplied by 5 to get some idea of what would happen. And so if we take a look at that and close this, I did the 50,000 times 3. I think I thinned by what? I think, well, I used 10,000 for burn-in and then kept only every 25 of the remainder. That one is up here. And it didn't have particularly pretty, so come on, open up. There we go. I suppose you could argue it was better in a sense, but it actually uncovered, even larger excursions from good convergence in a couple of these. You can see B, it's a little harder to tell what's going on overall because it kind of got squished down because there was one excursion over here that was really ugly. And in fact, if we go down and look at K, you will see that excursion in B corresponded to a period here where K basically got driven down to near 0 in here. Again, part of this is sort of, again, they're highly correlated, which is an identifiability problem of sorts. It means that, hey, it looks like maybe we can get combinations of A, B, and K that seem to produce roughly the equivalent fits, because you can see the deviances aren't markedly separating for the different iterations there, but they do poorly here. So there's probably a pretty nasty three-way correlation. Notice that our intercepts, alpha 2 and alpha 1, look pretty good out of this. Similarly, our standard deviation for our random effect is pretty clean. Okay, so brute force, if I'm going to do brute force, I'm going to have to go a lot more than 50,000, and that means waiting potentially hours for this run. So maybe I need to get a little bit, to finesse it a bit more than that. One of the things to consider here is if I look at this model, one of the properties here is I've got one component of the model that involves an asymptotic increase over time. And if we look at the data, let me scroll back up to here, notice that it's not that apparent that we're though the basic shape of that asymptotic function appears to be there, especially when I look at this less than or equal to 2 group, we might still be a pretty long way off from that asymptote, which means that asymptotic value B might not be very well determined. This is similar to the problem you often encounter with things like Emacs models where you don't have data that's at the asymptote. Under those circumstances, you would see, in that case, your Emacs and your EC50 would be highly correlated and would cause problems. Here, it's more the B and the K that would be that problem. And then it gets even further complicated by introducing this other intercept here. So I tried a couple of tricks to try and offset that, and in particular reparameterize it so that I was hoping that under the new parameterization the new parameters would be less correlated with each other and thus perform better. So one of the first things I tried, let's go ahead and open up one I call hands-on 3par1. Let me open up the corresponding model. Okay, most of the stuff in here is identical. Where things change is I took care of the reparameterization down. Okay, cut that out. Down here in where I'm specifying the priors. So you can see here what I've done is I say, okay, I'm going to reparameterize the drug effect in terms of two parameters I call B star and T star. T star I'm just going to put a fixed value on. And what I'm trying to do is construct a parameter that is more closely related to values within the observed range rather than something out at some asymptotic value that occurs in some hypothetical time to infinity thing. So what I've done is I set T star to be some value within our time range, and in this case I just picked the endpoint time of our study, 24 weeks. So you can see I mentioned T star is 24 weeks. And B star is going to be the value of that one term, that second term in the drug effect at T star. So that's where you see this. So B star is going to equal B times 1 minus e to the minus k times T star in that. Similarly, if I turn that around, I can solve for B. So anyway, before I go there, so you can see I set T star to be 24. B star is what I'm going to put my prior on, and that's the quantity that's going to get sampled in the MCMC sampler. And then I get B indirectly from that. So in other words, I kept all of the reparameterization is only exposed down here in this section. So I tried that to see what would happen. So when I try that, I open these up. Okay, this is with the smaller number of iterations. This is again 10,000 times 3, and gee, that didn't help a whole lot. You can see it's different, but it isn't necessarily better. B star, which is what's being directly sampled, and then B, which is calculated indirectly from that, don't look very good. A doesn't look very good, and K still doesn't look very good. So that didn't help me a whole lot. So I tried another one, but using the same general idea that I want to have at least one of the parameters is going to be more closely related to what we observe within the study itself. So let's go and grab another reparameterization that's actually not all that different. Where'd it go? Yeah, I call it repar 2 here. Okay, again, the change is all embedded down here in this section right here. So what I've done here is just slightly different. Recall before I had this B star was the B times 1 minus e to the minus k T star. Well, now it's A plus B. So it's basically the entire drug effect component of the model. And here, so the only thing I've added is this A term in here. So that's the part that changes as a result. The calculation of B is again slightly different because it involves A. See, I do have a question here that I just spotted. Question was, how does this parameterization allow e-drug to change with time? Now, I don't know whether that was asked in terms of the previous one or this one, but I think the answer is probably the same for either. It actually changes exactly the same because the only thing it changes is how the MCMC sampler, and particularly the Gibbs sampler in WinBUGS, what it treats as the primary quantity that it's doing the sampling on. But the actual model, in a sense, is identical. It differs slightly in terms of the prior, because I've now put the priors on these new parameters, not on the original, so there is some difference there. But the primary model, the likelihood function itself, is unchanged in here. Okay, so I did that in here. The logic behind this one is by putting the A on this, now what I'm really talking about is, in a sense, something that's more closely related to the observed difference from the placebo outcome in here. So again, it's more closely associated with the quantities we actually observed than the original B, certainly. And so we try that one. And when I take a look at that, again, this is using the 10,000 times 3 iterations here. I would argue what we get is a marked improvement in this instance. And essentially we've gotten that marked improvement by by parameterizing in terms of a quantity, this B star, that under the hood is less correlated with A and K in here. So if you look at the correlations under the hood, if you actually looked at pairwise comparisons of B and A and B and K, you'd see the correlations are still present between those quantities, but you would see less correlation between B star and some of those others, and that's improved our sampling characteristics a lot. Now, is this really quite enough samples? I'd argue probably not. But it looks much better if we look at, in fact, we can look at the, let's look at our estimates here. And here's our effective N, and it's still not quite enough. We've got some that are still fairly in the low hundreds here. What's our lowest one? Our lowest one, I guess, is our K at 132 here. So I would argue you probably still want to knock this up by a factor of 5 to 10 times that number of samples to have it good. But it's markedly better than what we saw with either the original parameterization or that first attempt at reparameterizing. Now let's actually, now that we've got this, let's step through. It's not going to, we can still make reasonably good inferences from this. We can look here. You've got your marginal posteriors here, so you can kind of get some idea of the values from that. And of course, we were just looking at here. We can see the values of our various parameters in here. I hadn't even really thought about any inferences I might want to make from these, but you can certainly see the values and their standard deviations and so on up here. Here you can look again, another metric in terms of correlations, and so, or I'm sorry, in terms of convergence. Again, you're looking for all of these things to be down close to 1, and most of them are pretty good with, again, A, B, and K are probably okay, but it'd be nice to drive the number of samples up so that it would even be better. And then our main diagnostics here again are fairly simple posterior predictive checks in terms of the predicted fractions of patients at each score level. And these are the so-called individuals. So I've taken the individual predictions for each patient and then calculated the fraction of patients then that are in each one of these, and I've done that for each MCMC sample so that I can generate posterior medians and 90% credible intervals, and then I've overlaid the values for the observed fractions of patients, and you can certainly see what we're getting here. You can see the general behavior across all of these, and it does seem to capture the relationship pretty well there. This is now doing the same thing, but in terms of the logit on these quantities. What's this? This is the population predictions. Again, because our sample sizes are so large, in this case they're 250 patients in the entire treatment arm, with a significant fraction at each score level. The difference between the population prediction and the individual prediction is pretty small here. Again, another one here in terms of the logit. Probably should have, I didn't do the cumulative probabilities. I probably should have done that. Also taking a look at our assumption that the random effect is normally distributed here. So I'm just doing a simple histogram on the left and then a QQ plot which compares with the standard normal on the right, and things are looking pretty clean in this particular case. That was all, yeah, that was all the plots I did on this thing. Let's see, we've definitely gone past our time here. There's certainly other diagnostics we might want to entertain. There's no reason at the level of the model to look at the question of proportional odds. We've sort of done that already at the level of the observed values. There are other things that could be problems, just like any kind of data. There could be some serial correlation present, and of course our underlying model assumes that conditioned on the patient's specific random effects there is no such serial correlation. So there would be tests we could do to try and look at that, for example. Trying to think of other things I would particularly want to do. We've kind of covered the fraction of patients at each score level. They're looking so good, looking at the cumulatives isn't going to change the story on that. But you could imagine coming up with other test statistics for doing posterior predictive checks on it. One thing we didn't do here is I could have taken that notion of the latent residuals and applied it here as an outlier detection strategy, because right now we're looking at these as averages of all the patients, so it doesn't ask the question of are any of them particularly unusual in any way. So we could do that. It would be another kind of diagnostic that you might bring into this. Okay, let me quit talking for a minute here, see if there's any last questions before I let you loose. Oh, I should mention I've posted all three of the models on the website. So you'll find there a zip file you can download that contains all three of these solutions in there, so you can sort of look at those for yourself. Okay, nothing's popping up there so far unless somebody's typing a long question here. Keep my eyes open for a minute. I guess on Monday, I think we finished up on our ordinal regression problem here. So I believe on Monday we're going to be kicking off on looking at count data. Let's see, we got a question here from Dana. What should you do if proportional odds is not valid? Then we have to start looking at a broader range of models. It doesn't necessarily mean we can't use logistic regression or cumulative logits, but then you have to start entertaining changing. Actually, let me pull up the slides real quick here. Let me go back to the more general discussion here. There's a couple of directions. Okay, let's see. Okay, which one do I want to look at here? Well, this is as good as any. Now recall in here the model, the basic model we're using is, so we're using logistic regression. So we've got our logit transform on the left side, and on the right hand side the model is written in terms of a intercept which can vary with the score, and a function which is independent of the score. So one direction that you can explore is having this function vary with the score, and that starts opening up a whole can of worms in terms of the range of things that you could consider. So it could go up to arbitrarily high complexity. You probably don't want to get too complicated there, but that's one direction for dealing with it. Another one is to look at alternatives to the logit link function, and consider things like probit or the complementary log-log, for example, are two approaches that are sometimes considered. So basically, it's talking about generalizations on one or both sides of this relationship that you look at here. So that's one way to look at it. Another direction is to go back to our latent variable interpretation of this and generalize on, actually let's go down to generalize on this side of it. Actually, did I guess I just mentioned that in the concept of the binary. We talked about various generalizations of a latent variable approach. So in this case, you've got a latent variable interpretation that makes use of the logistic distribution. And of course, the other cases I mentioned that associated with using a probit link function would be essentially doing it can be interpreted as a latent variable approach where the distribution is normal, and similarly the complementary log-log is associated, what do they call that, the extreme value distribution. And you could consider other possible probability distributions as the basis for a latent variable based model. So those are sort of three kind of categories of ways that you might start exploring. So it gets out into a fairly large, a large universe of possible models that would not adhere to proportional odds. Actually, one direction that I might point you to now that I think of it, let's see, is that the last slides? Let me point you to one paper too. I think it's in the list here. Let's see. Yeah, the paper here by David Lunn, Wakefield, and Racine Poon is a nice one talking about cumulative logit models. They use a case study where they actually play around with some different things that amount to violations of the assumptions in the simpler cumulative logit. In particular, they do look at a particular type of violation of proportional odds. In addition, they go further to deal with a fairly simple approach for dealing with serial correlation on top of it. So that's one worth looking at. And then the other place to go looking is, okay, where's the Agresti book here? There's Agresti's book here, and I actually haven't looked at it yet. I just put it in order for it, in fact. But Agresti has a new one out that focuses entirely on ordinal data. So I'll be curious to see what else that might have to offer. But it will certainly have ideas on other directions to consider. Okay, that was probably a lot more long-winded answer than you were looking for, but looks like that's it. So I'm going to go ahead and escape and let you do the same. Have a good weekend, and again, we'll be talking about count data on Monday. Talk to you then.